So first of all, welcome to everyone. This is NoSQL at Netflix. And you're probably wondering, first of all, why it says part 2. It's not because you're late and you missed the first part of this. I actually gave part 1 a few months ago at a meetup at Facebook and also at QCon London. So I didn't want to reiterate exactly the same content. So you can find that talk on Netflix's Tech Blog. This talk is going to sort of grow and add to that first talk. So they're sort of complementary and they add more color to each other. So feel free to look up that talk as well if you have a chance. Before I start, I wanted to give a special thanks to our OSCon organizers and especially Shirley Bales for bringing us here and making MySQL very comfortable. So I wanted to first give them a round of applause, if you can. And a few other announcements. We have about 5 people here from Netflix throughout this week. First of all, Adrian Cockcroft. Actually, Adrian, can you stand up? So Adrian's going to be giving the keynote tomorrow at OSCon Data. He's sitting over here and he refuses to stand up. Other people, Daniel Jacobson, I'm not sure if Daniel's here, and Matt McCarthy and Kim Trott are speaking later on in the week. Matt's going to be talking about our API. Our API is really important to our entire device strategy. And Kim and Matt are talking about WebKit. Both are really exciting talks. I'm just going to touch on some of that topic here in this talk, but I recommend you go check those out. So after thanking the people for bringing me to big data, my first slide is that big data is boring. And I'm not saying that to be controversial, but what I mean by that is our largest data set, for example, is our Tomcat logs. We have a log rotation script that pushes our Tomcat logs to S3. We have hundreds of petabytes of this data, and it's constantly being written. However, we don't read it, and we don't do anything with it after it's written. So it is our largest data set. It's just vastly not used, and it's just really boring. What we kind of are working on is more interesting. It's all about fast, available, customer-facing data. And as we think about global expansion, accessing that data on a global scale is going to become more and more important. So when I talk about fast or big data here, I'm actually talking about low latency, high throughput, customer-facing data, and if that data is not available, it's affecting customers. So any talk about our move to NoSQL and high availability storage starts with our story about moving to the cloud. So in 2008, we had a series of kind of outages that resulted in not being able to deliver disks. So this is back when we were a disk business, if you guys remember. We used to deliver DVDs in little red packets to you guys. So just to get a show of hands, how many people here have DVD subscriptions? I did say DVD subscriptions. I hope you guys caught that. And how many of you have streaming subscriptions? Excellent. How many of you have both? Whoa, that's excellent. So I hope you guys all notice that almost everybody has both. And that's good news for us. But it's also good news for you if you have our stuff. So we had a little bit of an issue delivering those disks, and we realized that our single data center was a single point of failure. More importantly, that data center was running low on cooling, power, and traffic capacity. So we needed to figure out what to do. We could either dedicate some of our resources to building out more data centers, but back in 2008 we were 500 people and about 150 people in engineering, 10 people in IT ops. Have you guys ever run in a company with 10 people in IT ops? Show of hands? Yeah, not many, right? So we were thinking, are we going to dedicate ourselves to delivering new features, or are we going to derail our product roadmap to build out these data centers? To put that in, to put an image to that, this is our API traffic per month. So this is API traffic to our Netflix API per month in billions. And as you can see, in October of 2010, we hit an inflection point. So in the 12-month period ending in January, we saw a 37x growth in API calls. So we're talking about 28 billions of calls. If we had stayed in our data center, this is how many calls we'd be able to support. So I actually had to thank Adrian for the slide. I didn't even know that was our data center capacity. And I was a little bit shocked, but having worked on the migration to the cloud, I can definitely attest to its value in scaling this. So to make a long story short, if we'd stayed in the data center, we'd be fighting fires like this. And so we outsourced to AWS. Now, before we talk about how Netflix actually uses AWS and NoSQL, I wanted to give you guys a picture of our web architecture. So on the top of this diagram, you can see some of our clients. On the left is our traditional web browser clients. On the right are like streaming clients such as the Xbox or the PS3 or mobile phones. Now, regardless of which client you use, you can browse movies and you can start a movie, right? But the architecture used to support that is a little bit different. For example, if you want to browse a movie on the web clients, on the browser clients, you will hit our elastic load balancers for traffic. And if you try to do the same on your mobile phone, you'll actually hit our API servers and the API entry points going through the elastic load balancer. Now, both of those paths will actually send you to what we call the movie discovery infrastructure. And I've shown them as two separate boxes here, but most of that architecture is actually shared. Just for sanity of this picture, I kind of drew them as two separate boxes. Now, regardless of which of these two clients you're on, you'd want to start a movie. So starting a movie actually routes you to our NCCP elastic load balancer. NCCP is what is our streaming server, and it actually helps you start a movie. So I've kind of divided our architecture in sort of three groups. You're either getting video playback, which is in the middle, or you're getting movie discovery either as a device experience or as a www experience. Regardless of which path you go through, before talking to Amazon's core services, we actually have a Netflix platform that my team built. And you can think of this as a platform as a service. It has a bunch of services like GeoIP filtering, cryptology, and internal discovery that we had to build because applications couldn't readily just use what Amazon had. So you can think of that as a sort of a platform as a service layer. And then, of course, you've got things like SQS, which is Amazon's queuing service, SimpleDB, and S3. To help you relate more to this, if you've used one of our clients, how many of you have tried the iPhone app? Okay, a good 20% of you, maybe. So you might recognize these screens. These are the 8 screens, or 7 or 8 screens you'd see if you had the iPhone app. So starting from the top left, you have the login screen. So if you have an iPhone, the native app launches WebKit, and WebKit gives you basically a web page with a login screen. When you log in, the first screen will take you to, again, serviced by WebKit, which is just a rendering engine for a web page. That'll deliver to you our homepage, our home screen. And then there's a little footer. So if you hit the genre listing, you can go to our genre page. You can also see your instant queue. And if you click on any of the movies, it takes you to what is called the video detail page, shown here for Arrested Development. And once you click the play button, we basically start video playback, which launches Apple's video player. So if you now remember that kind of architecture from before, which is basically our API ELB and our NCCP ELBs, everything covered with an orange border is serviced by the API infrastructure. So when you're doing any of those actions, you're talking to our API servers. When you hit the play button, you're actually starting video playback, and then you go to our NCCP servers. Now, if you've heard of if you've watched any of our other talks, a question that often comes up is, Netflix is an Amazon, but are you serving your movie streaming bits out of Amazon? And the answer to that is no. If you have any of these devices, when you hit the play button, you're coming to our servers in Amazon just to authenticate and authorize your device. And it's all secret sauce that we can't really go into, but once we authorize your device, we actually download sort of a DRM key for you. Then your device is also given a list of endpoints to CDNs. And your device will start trying to talk to one of them, and it'll pull bits down. And the bits that are being pulled down are encrypted. So what will happen is on the fly in memory, it'll decrypt those bits and buffer it, and then that buffer is what's used to service your playback experience. So that's just an overview of our architecture. It'll kind of help you understand the other slides that we're going to cover. So how do we use Amazon? What do we use it for with respect to this fast, available, customer-facing data? So we can look at the services we use in 3 groups. We have compute, which is basically auto-scaling. We have queuing via SQS. We also use simple email service and simple notification service a bit. And we have persistence, which is really the big data part. So how many of you have used Amazon or ELBs before, just to get a sense of that? Okay, so not that many, but about 10% of you seem to have used it. So as a primer for people who haven't used it, an Elastic Load Balancer is basically, as it sounds, it's a load balancer as a service provided by Amazon. When you create it, you use the Amazon's AWS console to create it. You get effectively an A record made for you. So you get a DNS name pointing to something we don't really know about, right? And Netflix maps a CNAME to this ELB. So in the example shown here, we have an ELB in front of our API process. And I'm not sure if this is really what the CNAME is, but you can imagine it being like api.netflix.com. Then Netflix registers a bunch of EC2 instances behind this ELB. And the ELB periodically polls the HTTP port of our instances to see if they're healthy. And there are a few more metrics or heuristics behind this, but effectively, the ELB doesn't want to route traffic to unhealthy instances. So that's why it polls your instances. To see this in a picture, imagine that you have a mobile phone, and it's trying to resolve api.netflix.com. It'll go to this cloud, which I call the ELB cloud. And that cloud actually has multiple instances within it, and Amazon controls that mapping. And I'm not sure how much of it is public, but there's a really good if you Google Shlomo Swidler, he's got a pretty good analysis of what actually happens behind the scenes. So what is happening here is that that node that sits in that cloud will then load balance your traffic to one of your instances per zone. So what happens is your device will connect to that node in the ELB cloud, and then that node will proxy a request to one of your servers inside one of the zones. And then your server will respond, and that response will be proxied back. Well, that's sort of the primer for ELBs. We started taking this a bit further in early January of this year. So we use CloudWatch. And CloudWatch is Amazon's monitoring service. And the cool thing about CloudWatch is that you can set an alarm in CloudWatch on some sort of metric on your EC2 instance. So for example, we use CPU limits. And we associate each alarm with an auto-scale policy. So here's sort of an example of a policy that we use. If the CPU on any one of our instances goes above 60% for 5 minutes in a row, we're going to add some number of instances, like 3 at a time per zone. Okay? And if the CPU drops below 30% for an extended period of time, we're going to remove a node from the zone. There are multiple metrics that are supported. You can use CPU. You can also use like data read or write operations, which is just a count. Or you can do the same in terms of bytes. Bytes in and out of disks on your EC2 instance. You can also do network in bytes, network out bytes, but we found that a CPU is the most reliable. So this is sort of an event flow for how we use it to auto-scale traffic going to our streaming servers. The streaming servers sitting behind the ELB publish data to CloudWatch. If an alarm is triggered, CloudWatch will look for one of the autoscale policies we have, and it will either add servers or remove servers. This is really what we have set up. This is basically our first attempt back in January to try this out. I don't know how far we've tuned this today, but this worked for us quite well. Our scale-up event effectively was average CPU above 60% for 5 minutes, and we could effectively scale up. And if the CPU dropped in any instance, well, actually we did averages across all instances. If they dropped below 30% for 5 minutes, we scaled down. And then there's this thing called a cooldown period. Effectively, the cooldown period is that after the ELB takes an action, it doesn't do anything else for 10 minutes. Otherwise, it could get into a really bad feedback loop. How does this work in practice? So I've had to block out some of the numbers here, but this is for when we launched the Nintendo Wii. The top graph is effectively our aggregate traffic for that device, for the Nintendo Wii, between January 29th and 30th of this year. The middle graph is the average or aggregate CPU across all the instances behind our ELB. We were basically aiming at a peak target of around 50%. So we didn't want our peak to go much higher than 50% aggregate. The third graph at the bottom is actual number of instances sitting behind that elastic load balancer. And what you can see is when the traffic peaked above 60%, a scale-up operation was called, and we scaled up the number of servers sitting behind that ELB. And we were able to pretty much be on target, around 50% aggregate CPU. And then in the second graph, when we dropped below 30% for an extended period of time, we scaled down. The first thing to note is that the size of the steps are different. When we scale up aggressively. We take larger step increments to scale up because we don't want to be without capacity. But when we scale down, we actually scale on one instance at a time. So that's why you see smaller steps going down. So this is effectively how we use elastic load balancing with CloudWatch, and it's been really effective for us. Aside from auto-scaling, we also use queuing. So we use SQS. It's effectively a queue. And just to get the terminology right, the SQS queue is sort of like a message queue. It's not a topic, if you're aware of what topics are. And a message is a message. So if you're used to it in the enterprise space, it's the same here. There are two different APIs that you can use. For example, you can create a queue, you can list queues, you can also delete queues. If you want to use a queue, you have basically 3 calls. You can send a message up to 64 KB in size on their queues. The default is actually 8 KB, but you can override that to 64 KB. When you receive a message, you can actually receive them in batch. You can receive 10 messages at a time. So your consumers will receive those messages 10 at a time, whereas your sender can only send 1 message. Your producer can only send 1 message at a time. And their terminology for acking a message, where the consumer says, I received this message, I've processed it, now queue, please remove this from your queue, is called delete message. So you actually delete it from the queue. Now, if you've used queuing, you might be aware of a visibility timeout. So what happens effectively is one consumer consumes a message and is processing it. That consumer hasn't deleted the message yet. A timer starts in the queue. And if that timer expires before the consumer is done processing, that message becomes visible again and another consumer can process it. So if you've ever used queues, you know that any use case that sits on a queue has to be idempotent. It has to be flexible to being processed again. And by default at Netflix, we use a 5-minute visibility timer. So we're really happy with SQS. Before we had SQS, we had tons of production issues at Netflix when we were in our own data center. For example, we were using WebLogic. I hope no one here is from WebLogic. But effectively, first of all, it's a queuing service written on Java. Java is a great language, except when you're writing memory-intensive sort of applications. So the prototypical use case for a queue is sort of like asynchronous writing, like application logging. So we were sending up to 40,000 messages per second for logging errors. So we're writing 40,000 messages per second to this queue. And what's sitting on the other side of the queue? Well, it's a consumer. And what is that consumer doing? He's writing to Oracle. Okay? Now, Oracle works fine, except when it doesn't. And when it doesn't, the consumer stops consuming. And the messages in WebLogic basically start growing. Right? So WebLogic has this thing called like a quota. Right? Or at least we implemented a library, a client library, which is a quota. And what that means is, we know that if we let that message queue grow, garbage collection is going to happen. It's going to cripple the WebLogic server, and then we can't drain that queue. We're basically hosed. And we were, like every week, we would basically bounce the server and drop everything on that server. So our producers were smart enough not to add messages once the quota was reached, and the producers would just drop the message on the floor, and in some case we would store it on disk. Generally speaking, it was a nightmare, and we had 3 people just managing that server. So when we moved to SQS, one of the best things in our lives was that there's no such thing as a quota. You can just keep adding messages to it. If our consumer died for a day and it took us a while to debug it, we weren't afraid of losing messages, as long as we could clean it up within 4 days. That's the only thing that you have to deal with, is that a message on SQS will be automatically removed after 4 days. We've been really, really happy with SQS. Now there are a few things on our wish list that we've asked for. One of them is, just like we can do a batch receive, we'd also like to do a batch send or a batch delete. And the main reason for that is, TCP teardown, right? We have tons of messages being sent, and we'd like to effectively not pay the penalty of doing cross-LAN traffic and TCP teardown. So we just want to batch more traffic, because we're doing basically WAN transfers. Another thing that we've asked for is better reporting. So one funny thing we ran into in SQS is called an empty receive when the queue has data in it. So one day I was awakened because we had 40 million messages in the queue. And so we spun up a bunch of consumers, and those consumers were doing empty receives. How can you make a receive call and get nothing back when SQS is telling you they've got 40 million messages? So there's a reason for it, which I can't really go into here. Maybe if you buy me a drink, we can talk about it. But effectively, Amazon has fixed this issue to a large extent. But we'd like some visibility into how many empty receives we're doing. And they're going to make this available in cloud below. And we're constantly reprocessing the same message. We would never know. So we've asked for that as a CloudWatch metric as well. And they've agreed to make it public at some point. So let's talk about persistence. The big question with persistence is which data store to use in the cloud. And to solve this problem, we put some of our best engineers on this problem, thinking about how to solve this. So when we first moved to the cloud, which was back in 2009 and 2010, our initial requirements were that whatever data store we picked, it were hosted. We were busy enough moving stuff to the cloud. We didn't really want to host our own data store. We also wanted a managed distribution model, which means that we wanted failover and failback and recovery to be taken care of for us, either by people or by the application itself. We wanted something to work in Amazon, and from the CAP theorem, we wanted something that was highly available. Being an entertainment web service, we don't care about consistency that much. We really care about high availability. And that's another topic which would be one entire talk if we go into why NoSQL makes so much sense. But that's really what we were looking for, high availability in reads and writes. And since most of our data is centered around either a customer ID, a movie ID, or a combination of a customer and movie ID, we just wanted to do key lookups. In many cases, we are using what is called secondary indexes, but that's our main use case. So we don't really have needs for joins and complicated root bys. So back then, we picked SimpleDB and S3. SimpleDB is an Amazon service, and it was targeted as our replacement for Oracle. We also used S3 for data sets that didn't fit into SimpleDB. So SimpleDB has a few limits, such as a column can't hold more than 1 KB of data. So they don't have a concept of like a blob. So for blob type of data, we put that in S3. There was a caveat when using S3. We do not use S3 for any latency sensitive or customer facing traffic directly. We hide it behind a cache, and we hide the writes to it behind asynchronous writers to the largest extent. So what do we put in S3? We put video encodes. So you know that we show you movies, but we have a job that actually encodes those movies from mezzanine files. We today generate between 40 and 80 different encodings for any video mezzanine that we get. And we push all of that data up into CDNs. We also have streaming device telemetry logs. So every time that you use Netflix and you connect with one of your devices, that device is reporting back home to us, telling us if you're having issues with your ISP or a CDN, what your bandwidth is, the number of errors you're getting. So that's kind of verbose data. So if you do call into us, our customer service already has access to that log and can help figure out what the problem is. And many times we have issues, it's usually ISP choking or some problem with the CDN. Another thing that we store in S3 is called our compressed rental history logs. So every movie that you ever watch is stored in our rental history. So we have billions and billions of records at this point. This was great when you were getting DVDs because you were not increasing the count more than 3 or 4 times a week on average. But now it's you're each increasing it 10 times a day. So every day you're watching a movie for a few minutes, and guess what? We're storing it. So the problem with that is that data set is growing much larger for each customer, and the response times for fetching rental history for each customer is growing. So to work around that, we compress the tail. So this is called tail compression. We basically take all the movies you've ever watched, compress it into one single blob, and store that one blob in S3, and we run it by a cache. And we preemptively fill that cache. So this tail compression is a good way to work around long tail history, such as rental history. So let's talk about SimpleDB. The terminology behind it, it's a key value store. So you have something called a domain, which is equivalent to a hash table. And if you're from the relational world, it's effectively a table. An item is effectively a row. The item name is a key. And attributes, it's a sparse schema, but attributes are like columns. You can think of them as columns. Let's look at an example. So say you were to build a soccer player domain. So in this soccer player domain, I'm showing you 3 rows. The key part of the key value is just some sort of UUID or GUID. The value part is a bit more complex. The value is actually a set of attributes. Each attribute has a name, and each attribute also has a value. So for example, the first row, there's a name for Harold, and his last name is Kuhl. What you'll notice here is that the third row doesn't have any data for a nickname. So it's a sparse table. It doesn't waste any data, any space on disk. The other thing you'll notice is the team's attribute has multiple values, and those multiple values are effectively a set of values. Now we don't use either of those 2 features because they defy they violate the first normal form, and I'm going to talk about normal forms a little bit later. So SimpleDB offers a range of consistency options. So you can either use it as a, you can use eventually consistent reads, but you can also do strongly consistent reads. Everything that's stored here is a string, so there's no concept of types, and everything is a UTF-8 string. The types of APIs you can call for management of these domains is create a domain, delete a domain, list domains, and you can also get domain metadata such as how many keys you have or how many attributes you have. In terms of accessing data, you can do singleton accesses such as getting an attribute, putting an attribute, deleting an attribute. You can also do bulk calls like a batch delete or a batch put. You also have the option of doing a subset of SQL on these domains. As I mentioned, you have options for consistent read, and they also have a optimistic locking type of API. So when we were moving to SimpleDB, and now as we consider moving to Cassandra, we're encountering some of the same problems. We still have a few use cases stuck in Oracle, and those use cases have to be translated from a relational model to a key value model. So let's talk about some of the challenges there. So first of all, when we think of relational databases, we think of relations. But, and so when you think about relations, you have to kind of think about normal forms. When I started this work 2 years ago, people were just saying, just denormalize that data. But there's some dangers, and some people forget those dangers in the hype around SQL. So first of all, the first normal form says that every column has exactly one value. It cannot have multiple values, and it can also have 0 values. And this is just a definition of relational databases. This is a property all of them have by default. So when we tried to use the multi-value field, it caused a lot of problems because it didn't really work with the relational model. The second normal form is very important. So imagine that you have like a part warehouse table. So you have warehouses, and they can store multiple parts, and any part can be stored in multiple warehouses. So you kind of have to, if you try to keep this as like a denormalized schema, you run into a series of problems. So some of the obvious stuff is that you waste a lot of space, because if for every pair you have to store that information. So every part stored in warehouse A has to repeat like warehouse A. So that's kind of a waste of space. The other problems are like data inconsistencies with updates. So if you forget to update the warehouse for a given part, it's possible that you would have that same part stored in so going back to this, the problem here is actually the warehouse address. So for a part stored in warehouse A, you could change its address, but for a different part stored in warehouse A, you could forget to change the address. And now you've actually got an inconsistency in updates. As well as you could have what's called a deletion anomaly. If there are no parts at all, you've lost all the information about the warehouse address. The right way to fix this is to, in fact, normalize it. There's a similar problem with like a third normal form. So the effective guidance that we've given inside Netflix is that you can move anything that has a one-to-one relationship. Most of e-commerce data is actually in a one-to-one relationship. But there are some tables that have many-to-one or many-to-many relationships. You cannot denormalize that. You will just get into a lot of trouble. So for those very few use cases, you have to kind of keep that in a relational schema. It turns out that we've moved all of our web scale data to a denormalized or to a key value store. Last year, from February to December, we moved all of our data and traffic so that by the end of December, 95% of our traffic was coming from the cloud. What's left in our data center are a few tables that are not one-to-one. So lucky for us, everything is already a one-to-one relationship and is viewable by either a key lookup of a user, a movie, or a company. Other than the relational side, other stuff people get used to with respect to Oracle are things like transactions, locks, sequences, triggers, clocks, a structured language, other things like constraints. Unfortunately, none of these, or most of these, are not available in key value stores. And when I talk about key value stores, I'm talking about things based on the Dynamo model or also SimpleDB, either of those two. So, for example, you don't have joins or group binds, so what do? We just do this in the application layer. And of course, you can only do this for small data. If the data is very large, materializing a join over the network is very painful. Another thing that we do is that we compose relationships in the application layer, and this is very common if you've worked on web apps. You do that all the time without even knowing it. We don't have transactions. SimpleDB does have a conditional put delete, and there is a way to do this in Cassandra. The funny thing is, I think most people don't talk about it, and I tried to explain this at the first version of this talk, and nobody understood. So I'm not going to make an attempt. If you're really curious about how to do this in Cassandra, come talk to me. There's no schema, so this is a little bit of a problem. Whether you're using Cassandra or something else. Two applications. One, well, Cassandra may not have this problem. I have to check it, but it depends on the serializer that you're using. But say SimpleDB, just an uppercase, lowercase problem, or a misspelling. I mean, it will look for it. It won't find it if you're doing a lookup, and it'll say there's no data for this, but it won't complain that you've misspelled it or you've used the wrong case. And definitely in Cassandra, if you misspell something, you're not going to find it, it'll say there's no data here. So some sort of schema would be very useful, and we've thought about putting it in our data access here. Other things that we have, for example, are sequences. Like we have sequences all the time in relational schema. We don't have those in the cloud. We do now have a Zookeeper cluster, and we could use that to generate sequences, but we don't want to depend on a separate system for something like this. So instead of using sequences, we just use GUIDs wherever we can. And sometimes when we have to transfer data back to the data center, we have to do a little bit of extra work. The other thing that sequences are used for, other than just being used for uniqueness, they're also used for ordering. And we don't use sequences for ordering, we use timestamps, and we just make a best effort, knowing that time can drift. So going to that specifically, no clock operations, what do? We use NTP, so we have NTP running between our regions and our data center to keep things in sync. We don't rely on them being totally out of sync, but we do have alarms if they do go very out of sync, and that rarely happens. So we just don't mind having things be slightly off by time. One of the main things that we've used as Netflix as a guidance is consistency, not accuracy. So what that means is we want to give you a consistent answer. Is it, in terms of a global clock, the most accurate one? No, because as we go globally with things, we're going to have data pushed all over the world. We can't keep those clocks in sync. And if we rely on something like vector clocks, there's going to be a lot of delays. So rather than doing that, we just are going to shoot for things being consistent, a consistent answer being met, but it may not be the most accurate one. In terms of constraints, we just live without constraints. We have no uniqueness constraints, or foreign key constraints, or integrity constraints. Applications have to sort of do this themselves. And one thing we've realized in self-healing systems, since we don't have the rigidity of ACID, sometimes we need to have consistency checkers running. And that's just normal. Some people are shocked by doing this, but that's what a self-healing system is. It's going to solve the problem later, and we don't really sweat it. So there's a lot of detail I didn't go into in this talk. It'll put half of you to sleep, and the other half might be really excited. But just have a look at some of these resources. Mark Atwood's Guide to NoSQL Redux is a really cool one. I think about that stuff a lot coming from a search background. I've given this talk earlier, and there's a tech blog about it. And there's a white paper if you want to go into details of how you actually move this stuff to NoSQL. So Cassandra, I'm not actually going to talk too much about Cassandra here. I'm just going to kind of mention the data model. So first of all, the terminology behind Cassandra. How many of you have used Cassandra? Okay, so this is what I've noticed. It's still a kind of a small community, and we're looking for Cassandra developers. So if you're interested in working on Cassandra, come talk to me. It's still something in growth. And we are one of the big proponents of moving it. And I recommend Adrian's talk. He's going to talk about Cassandra. So in Cassandra, you have a key space, which is like a schema. And certain things attached to a key space have to do with, for example, the replication factor. You have a column family, which is a table. You have a row. That's pretty self-explanatory. The row key is a primary key, and a column is a column. We used super columns earlier, but have gotten guidance to move away from them, and so we don't use them much right now. We moved whichever column families were using them to a different model, to basically the standard columns. Alright, so this color scheme is going to really test your color blindness. So this is a key space for Netflix, and I've got two rows here. How many of you said have used streaming? Right, across more than one device. Okay, great. So one thing that we do is every time you watch a movie and you veer away from that movie, we store where in that movie you were watching it, so that you can pick up from that point. And until very recently, until very recently, we were keeping those bookmarks in sync across the United States. So we had a data center here, and we had a data center in, we were using Amazon data center in the East region. And every time you watched a movie, some of your device traffic was going to the US East region, and some of it was going to the, our data center in the West Coast. And we were keeping your bookmark in sync within 2 seconds. So I helped build that infrastructure. It's kind of an interesting problem. So when you watched a movie, we would store across these two data centers where you were in the middle of watching it. So the way we use Cassandra for bookmarks, and it's still in the development stage, is that we have a column family called streaming bookmarks. And for SID, which is my row, I have some part in Tron and some point in TrueGrid where I last started watching it. And as many movies as I have, that's how many columns I'm going to have. And we don't expect people to have billions of columns. We've heard Cassandra can handle it. But we do expect them to have tens of thousands over their lifetime, because people are watching lots of movies. And then here, the second one has Babe, and he's 116 minutes into that movie. So this is sort of the data model, and it really maps very cleanly from SimpleDB. So it's a very easy transition for us to move from SimpleDB to Cassandra. So where does this leave us? Our original expectations of Cassandra, of our data store, was that it was hosted. It had a managed distribution model, worked in AWS. It supported high availability. It handled a majority of use cases for high growth traffic data. So most of those have stayed, except for the hosted part. And this is why, because we have a lot more requirements. So when we look, what other things do we need? So one of the pain points of using SimpleDB, the first one is auto sharding. It doesn't auto shard. We actually have to shard our traffic to SimpleDB. We have a terabyte of customer data that customers are accessing in SimpleDB. We've sharded it across 1,000 domains. That's kind of a pain in the butt. So we don't really want to be managing that. And for heaven's sake, please don't come to me as an engineer and say I need to reshard my data, because I don't have the time for it. So this is something that we're looking very closely at Cassandra for. Now, I've put here that S3 also auto shards. Has anybody run into repartitioning in S3? Has anybody used S3 here? No? A few people, and none of you have run into latency problems where stuff just went totally out of whack. If you read their S3 best practices, they tell you something about putting a unique number in the front of your key. I mean, have you guys wondered what that means? Not really? All right. So they partition like a modulo on that number. And they've got an unknown number of buckets sitting behind it. Or I should say partitions. And this is kind of what's already written in their best practices. That if you want to get the best performance, you're going to put like a unique number in front, which is not like a time, but a number that is sort of like a random number. And it's going to help distribute the load within their internal partitions. So they do that. So S3 is great for that, except when they do ever encounter repartitioning, you're in trouble. The other thing I'll mention here is auto failover and failback. So SimpleDB and S3, they all have that functionality, and we've been really happy with them. There were a few outages recently, which shows that they did not have automatic failover and failback. But they're fixing it. Cassandra does have that as well through their read repair and Merkle tree anti-entropy processes. And then we've gone a step beyond that, which is that we actually have implemented something we're hoping to commit back soon, having to do with taking backups of the commit log and of the SS tables and recovering a cluster from that. So we should be committing that back to the community fairly soon. We also want speed, right? So SimpleDB, how many of you people use SimpleDB? Okay, so one person, 2 people, all right. So it's fast, but maybe it's fast for Netflix, right? I don't know if it's fast for everybody. And we had to work very closely with them to make it fast. S3 is not fast. I'm not going to lie about it. It's pretty slow. And Cassandra, right now, we're trying it out, and it seems pretty good. I took a M24XL instance on Amazon, and I pumped writes into a cluster with a replication factor of 3, and I was able to see a consistent write throughput of 4,000 writes per second per node. So if you have like 100 nodes, you're doing 4,000 writes per second, like per client writes per second per node into a cluster times 100 nodes. So you can get really high write throughput into these clusters. Now, what about the reads? Everyone's heard that reads are a big pain. So another commit back that we're doing, actually we've already done in 0.8, is using off-heap row cache. So that was committed by one of our developers. Another really important feature for us is cross-region data storing. We've told Amazon this a few times now, and I think they're starting to listen to us. But the thing that we like most about Cassandra is the ability to play with the snitch and the replication policy. Okay, so I'm getting the signal to wrap up, which is great because we're almost at the end. This is the most important slide of this conference, if you ever see a slide. If you want to work on the Simian Army, basically the Chaos Monkey, or the Netflix platform, or Cassandra, come talk to Adrian or myself. We are both in cloud systems. If you want to work on video discovery, talk to Daniel Jacobson later on. If you want to work on video playback, you can talk to Adrian or I. That's a great team. Work very closely with them. And if you want to work on stuff that is developed on the partner products, right. So that's the end of my talk. Any questions?